Hi there, guys. Well, we're about to do 2B, and 2B is back on familiar territory. It's working with quadratics. And we're going to talk about three different forms of quadratics, their shapes, concave upwards, concave downwards, that kind of thing, lines of symmetry. That's what we're working on for this one. Okay, so this is 2B from the Oxford AAHL book. And just to note, I was just looking back, that last video was a pathetic 27 minutes long. So let's see if we can keep all of these down to under 30 minutes, perhaps. Okay, so there's a little start. This starts off with special functions in their graphs. This starts off with an investigation. You know, these investigations are good and they should be getting you thinking about potential directions to shoot off in for your IA, for your internal assessment. I'm not going to do that right now, though. I'm not even going to do this. About parameters A, B, and C, though I'm kind of going to go into that. I'm going to do this, okay, where it talks about the standard form of a quadratic, the vertex form of a quadratic, and the intercept form of a quadratic as well. Now I'm going to put these, or I have put these rather, into Desmos. I mean, if you don't know Desmos, I'm sure there's other online graphing programs which are really good as well, but this one is just particularly neat. And you can type in all of your things over to this side. Ooh, let's type in y squared equals to x and see what we get. Oh, that's what we were talking about in the last one, in the last exercise. There's our graph, which can be split up into, I don't know, let's say, let's see if I type in square root. Oh yeah, square root of x. And the bottom half is going to be y equals to minus the square root of x. There we go, the bottom half. Okay, so I mean, this is super easy to deal with. So anyway, I've just set up the three forms, three interesting ways of putting down quadratics. And the one on the bottom, let's just play around with this with my keys. So this one on the bottom here, this purple one, that's your normal form. So you normally used to putting A there and B in front of this, and I just haven't done it just at the moment, and C at the end. And there you go, that's just a normal form of a quadratic. Of course, you can solve quadratic equations by setting the y as equal to 0 and finding the roots of quadratic equations. So roots or solutions, when we set the equation equal to 0, or sometimes they're even called just zeros, can be solved by using the quadratic equation. I expect you to know the quadratic formula, so for solving quadratic equations. So I'm not going to go into that just yet, but it will turn up here. Okay, so we've got other ones here. We've got this form. Let's just get rid of that. Oh, I forgot to say about that. Y equals x squared. So you can write an x squared really quickly by using the circumflex, which is shift to the sixth, the little hat. So we've got x squared. We've got, what did I say? Plus 3x and minus 2, I think I wrote. So there's that graph. Interestingly, and I'm not going to explain why in this case, but interestingly, if we change this to a minus, it just flicks it across to the other side. That's just something to think about. We have a plus here, takes you to the left-hand side of the axis. We've got a minus there, takes you to the right-hand side of the axis. Okay, I wonder why that's happening, but I'm not going to go into that just at the moment. Okay, let's have a look at this form here. Now, you're probably used to this. Let's get rid of the A. And so this is our, what do they call it? Root form. They call it intercept form. Okay, so I mean, that's what the book is calling it, obviously. So intercept form is this form here, and you can see that if you put in 1 into this, you're going to get out a 0 from the equation, because of course, if you put a 1 in, this will be 0. Well, I think way 1 is 0, and this is just obviously a times in between here. Have a look, Desmos writes the times as a dot, but if we don't put anything, it's still times. So when you put in 1, you get out a 0, and also if you put in minus 2, you get out a 0. This should be all pretty simple for you. Okay, now if you want to scale this whole thing up, if I put an A there, it hasn't changed, but let's play this one now. You see as A gets bigger, it gets steeper, and as A gets smaller, it gets, hang on, there we go. As A gets smaller, so less than 1, it gets less steep, and of course when we go to negatives over here, when it gets to 0, we just get a flat line, not an interesting quadratic. And then when we go to negatives, it turns upside down. So this is called concave downwards, and this is called concave upwards. Okay, so this A in front is just creating a stretch of our function. And again, if we decided to, I don't know, call this f of x instead, then we could equally say, I wonder what A lots of f of x are. And A lots of f of x should be exactly the same as me putting in here A in front of this one here. Oh no, hang on a second. I've sort of doubled up on that one. Okay, so there's f of x. And if I put an A in front, or basically if I times this whole thing by A, then it stretches the whole thing, but the zeros stay in the same place. Okay. Okay, then in this one, let's get rid of that now. Let's get rid of this. Let's get rid of this. Okay, so now in this case, this is called our vertex form. And so you can see it's in a completed square form. Hopefully you know about that already. I'll go into that a little bit into this exercise as well. But we can obviously get rid of the 1 here. So this vertex form here is basically telling us quite quickly where the vertex is. In other words, when I put 2 in here, I'm going to get out 0 from this, and that's the lowest number possible I can get out from the expression which I've highlighted there. Okay, because it's always going to be positive. So the lowest number I can get out there is a 0, and that occurs when x is equal to 2. Now, when x is equal to 2, we see that y becomes equal to 1, because this thing in the center is going to disappear. So that gives us our vertex here. So when we put in x is equal to 2, we get out y is equal to 1. Okay, so this form here tells us the vertex, the bottom part of the graph, okay, the nadir, the low point, the apex, the vertex is what we normally call it though, okay? So it gives you out the vertex if you take the negative of this, okay, and then write this down for y. So the coordinate point there is coming out as 2, 1. Okay, that's our coordinate point. So if I change this just for a second, if I change that to A and B and just added some sliders for that, so let's add some sliders for this, then obviously that point is going to change, right? There we go, there's A now equal to 2. But if I make A equal to 3, it's just moving to the right. And if I make it negative, it's moving to the left. Now that basically would mean a plus A here. So if we put in A plus 2.1, then minus 2.1 is going to give you a 0. Okay. And likewise with B as well, B is just taking it up and down there. But there we go. That's our vertex. Our vertex here would be at minus 2.1. So that's probably quite difficult to see. I'm putting in sort of 2 negatives there because there's obviously a negative in front and a negative there. Let's just focus on the positive just for the start, okay? So basically, if this is 2, then x is equal to 2 is going to give us the bottom point. Okay, so that's vertex form. Now, I can also put a number in front of this if I want to. I can put 2 in front of that, and it will make it twice as steep, but the vertex will stay in the same position. If I say for this, let's just put 1 in. Let's take it back to there. So I can put a 3 in there, and that will make it 3 times as steep. It's perhaps worth looking as well at the original quadratics. So if we look at, say, for example, y equals x squared, so our most basic quadratic, it's perhaps worth just looking at the coordinate points. We've got 1, 1. We've got behind. We've got 2, 4. We've got 0, 0. We've got minus 2, 4. They're all points which are on our graph. Now, if you times this whole thing by 2, then those coordinate points are going to times by 2 as well. So you can get 1, 2, but only the y part. Okay, so we've essentially doubled f of x here, going from x squared to 2x squared. So what's going to happen is our heights are all now twice as high up. And that one's just kind of missing, but there we go, it's now twice as high up. So all of the heights are now twice as high if we just put a 2 in front. So that's just a vertical stretch which is happening. Now, that's often quite useful to see that basically if you've got a distance 1 across and 1 up from your bottom point to somewhere else on the graph, then we basically know the coefficient of x squared is 1, if you can see that happening. That's why that's kind of interesting. But if you can see from the bottom point that to get to this point up here, let's put 2 in there, to get to this green point, we need to go 1 across and 2 up, then that means we're going to have 2x squared. And it's often that you can see those kind of patterns that might turn up somewhere as an idea. Okay, so well, we're going on a bit here. I am at least. Okay, so lines of symmetry as well. So this, let's actually steal this here for a moment. So lines of symmetry, I'm not going to do that. I'm going to do this. So lines of symmetry can be found from the quadratic formula. So you know that if ax squared plus bx plus c equals 0, not equal to y, equals to 0, we're trying to find the roots. And here you can see there are no roots, but they could be complex roots. They could be square roots of negatives. I'm not going to go into that just yet. But x in this case is going to be equal to minus b plus minus b squared minus 4ac divided by 2a. And hopefully you've seen this before, and you might even have seen the proof of that by using completing the square, technique of completing the square to get to here. That's a really good page of algebra. In fact, you can do that. Okay, now why I've put that up there is because this formula here, I don't really remember from that. I remember from this. Now, so it's giving us our line. If we've got an equation like this, it's giving our line of symmetry as equal to minus b over 2a. And that's kind of hidden in. Okay, and the reason why that gives us our line of symmetry is because the roots are either a certain way further on from the line of symmetry or a certain way back. And that's less easy to see from this one. And if we say, for example, had this quadratic here, we can see that we have 2 roots, and one of them is minus something from the line of symmetry, and the other one is plus something from the line of symmetry as well. So to get to here and here from the line of symmetry, you're going to need to subtract or add the same amount. And that's this bit here, albeit that we're dividing that as well by 2a. Okay, so this is really minus the square root of b squared minus 4ac divided by 2a, and this is plus that thing. But basically all of these parabolas, so that's the name of the shape for your quadratic graph, so that all of these parabolas are symmetrical about a line of symmetry, and it's hidden in your formula here. It's this thing here. Okay, so right, without further ado, let's see if we can get on. Okay, so let's look at example 4. So, example 4. So first of all, it says state the concavity of the function. So basically, is it concave upwards or is it concave downwards? And we can see in this case that because there's a minus in front of the x squared, that's the thing which controls the shape. This is a positive quadratic. This is a negative quadratic. I'm not going to go into any more detail in this case. I think you should know about that already, to be honest. So this is going to be concave downwards. And for part A, it says find the equation of the axis of symmetry. Well, again, we just need in here the bit at the front. So the line of symmetry is going to be when x is equal to, so it's the horizontal distance along of this thing here. So what have we got? We've got b is 4, and minus 4 divided by and then we're going to divide by 2a, so 2 times minus 4. So that's our line of symmetry. This was just to find our roots. It comes from just doing this and ignoring the other part. So that's how I would remember that formula. So in this case, we're getting minus 4 over minus 4, which is equal to 1. So we have on our graph at 1 a line of symmetry. I don't know where the roots are. I know that this is something like this, but it could be, I'm not sure where that is. So that's our line of symmetry of the graph. Okay, right, let's get rid of that. Let's look at part B. It's looking for the vertex. Well, the vertex will come from putting the x value from the line of symmetry. So I don't know if that's our line of symmetry. If we put in that x value, which we now have, which is 1, I think we had. When x is equal to 1, we should get out the height, and that will give us our vertex. Now, there's lots of ways of doing this. This is just one way, and it's the way you're being encouraged to do this question, because you've followed on from A. Some of you might know differentiation, some of you might know completing the square to get it into vertex form, but we're just using the equation for the line of symmetry here, or the axis of symmetry. Okay, so if you put 1 into this function here, we've got when x is equal to 1, we get out y is equal to minus 2 plus 4 and plus 1, which is giving us 3. So we're getting out the vertex point of 1, 3. Okay, and for the next bit, it says the domain and the range. Well, you can put any x value you like into here, and you can get a lot of y values out, but there's a certain amount which you can't get out. So the x values you can put in are just all of the real numbers, closer to show that it's an R. Okay, and the y values which you get out are, well, going through the point 1, 3. We know it's a negative quadratic. I actually know that it also goes through the y-axis intercept of 1, because when I put in 0, I get out, and these terms disappear, and I get out the answer of 1. So I know it's going to go through here roughly. It's going to look something like this. And it's pretty tricky to write on my screen like this. So it's going to look something like this. Okay, I'm going to go through 1 there, and I don't know where the roots of this are just yet. Maybe, actually, we're not being asked for that in this question. So the heights that we can get out are, well, y belongs to the real numbers, but only heights below 3. Okay, so where y is less than or equal to 3. We can get a 3, but only that's our maximum. Okay, and for part D, it says find in vertex form, find the quadratic equation. Now remember that's y equals a, and we've got x minus 1. Okay, because if we put a 1 in here, we need to get out a 0 from this bracket. So squared, and then we've got, what have we got on the end here? We've got plus 3, okay? We've got plus 3, that's the y part. So when we put in 1, this disappears. That means the whole of this disappears. That means we get an answer of 3. And that's the lowest that we can possibly get. Sorry, it's the highest we can possibly get because it's negative quadratic here. So there we go. That one's pretty much solved. Apart from we need to work out what a is. And because there's, when we multiply this out, because there's only one way of getting x squared, okay, when we multiply out those brackets, we'll get x squared minus 2x plus 1. But because there's only one way of getting x squared here, and it's a times by the x squared, that means because we know the coefficient of x squared is minus 2, that the a must be equal to minus 2 as well. So minus 2 there, x minus 1 squared, and plus 3. Now, okay, you can skip ahead if you want to here, but I do think that you should be able to work out that last part of the question. Just check that I have got it right. Yeah, okay, so we've got that one right. And I think you should be able to sort out this last part of the question without following those 3 steps to start off with by using completing the square. Now, so this is just a quick recap on completing the square. And if you haven't done this before, it is really worth spending a little time and checking out some videos on how to do completing the square. So in order to do this one, this is just a recap, a refresh. We'll say y is equal to, basically what I'm going to try and do is get x on its own here. And I'm going to do that by completing the square with these two terms here. So first of all, I'm going to take out this factor of 2. I'm left with x squared minus 2x. I'm just going to leave 1 on the end for the time being. And I'm going to complete the square with this bit in the middle. This is the part where we actually do completing the square. This is the same as x minus 1 all squared, because I know that that generates x squared, and it also generates minus 2x, but it also generates a plus 1, which we don't want, because that's not in this yellow bubble here. So I'm going to take the 1 off, and now those two things in yellow are the same, and that's the completing the square technique. Okay, so I'm going to put my minus 2 outside the front, and I'm going to need brackets there because it's the whole thing there in yellow, and I'll put the plus 1 on the end. Okay, I'm pretty much there in terms of vertex form. I just now need to multiply that out. So 2 lots of x minus 1 squared, and I've got minus 2 times by minus 1 gives me plus 2 there. I've got plus 1 on the end, and that takes us back to the same thing, plus 3, same thing which we had via the other way of doing this question. Okay, and that was just a quick recap on completing the square. As I say, if you don't know how to do that, then check out a couple of YouTube videos because that's a really useful technique. Okay, so next part, sorry, where I messed up earlier. Okay, so example number 5, I think I've got 2 more to do. Right, example 5 here. So now this is a problem in context. A calculator company's profits in euros are modeled by this function. Seems pretty straightforward, this question. They give us a function and they say x is the selling price per calculator, and then find the price that generates the maximum profits. Now, it seems to me like this is going to be something like this. I don't know quite what it's going to look like. I think that's going to hit way down here, minus 12,000. And this is going to be your profits, and this is going to be your x. And we need to find this top point here. So it says x is the selling price of the calculator. It says find the selling price that generates the maximum profit. So that's this. That's the line of symmetry. And then the maximum profits. So that's this. So this is the same as the first question, just the parts A and B to that first question. And justify your answer. Well, I guess we'll justify the answer by saying it's concave downwards, or in other words, this is a negative parabola. So that's why we're going to have a maximum turning point in this case. So that's kind of done. Right, so let's get rid of all of that and let's work it out. So remember that the maximum value of x here would be the minimum, no, not the maximum value of x, the line of symmetry. Or maybe we can say that the line of symmetry is x is equal to minus b, so minus 1400 divided by 2a, so divided by 2 lots of minus 20, and what's that? We've got 1400 divided by 40, so 35 there. So that's x is equal to 35. So that's the line of symmetry. So that's the price that we need to charge. So I don't know what that is. Maybe it's euros. In fact, it is. Okay. And then we were looking for the maximum profit. So we're going to need to substitute that into here. I mean, that's pretty straightforward. You can do that. 20 lots of 35 squared plus 1,400 times 35. Take away. I mean, you can do that, right? Okay, now that should give you your maximum value. Okay, that question is done. And let's just have a look at their justification there. They say, since a is less than 0, the quadratic is concave downwards, and the vertex is a maximum point. Yeah, it's just talking about the shape of the graph. If you want to come up with a sketch of that graph, that would help bolster your explanation there. Okay, right. There's a little bit here about some extra cultural learning. Talks about an Islamic mathematician looking at chopping up bits of cones to get parabolas. Oh, and hyperbolas as well. Hyperbolas, as I was saying, hyperbolas are graphs which look like this. I've just Googled it. So hyperbolas, I was kind of doing really rubbishy graphs. So yeah, hyperbolas are looking like they're saying like this and like this, or like this and like this. Okay, let's get rid of that then. Okay, so what was the book saying? There's a bit of cultural knowledge there. I thought it was also interesting. If I've still got it up here. Um, the person who sort of developed a lot of the mathematics around the Cartesian grid, which we take for granted, the XY coordinate grid is Rene Descartes, and there's lots of interesting stories about him. And he's coming from the era just before Newton and Leibniz, and Newton and Leibniz were the competitors. I know in a previous um, video I was talking about Gauss as well, but if we go a bit back in time, we can find Rene Descartes, and it's kind of interesting his end of life. I found this was something I just learned today as well. So I like this little bit here. It said Descartes arranged to give lessons to Queen Christina of Sweden after her birthday. So this is a mature lady. This is not a child. And he arranged to give her lessons 3 times a week at 5 a.m. in a cold and drafty castle. It soon became clear that they did not like each other. I wonder if that had anything to do with him getting up at 5 a.m. or even her as well. Okay, in fact, he was there to discuss philosophy and to discuss, I think, ideas about love. Okay, so I mean, he was a bit of a generalist, and he also came up with, I think, therefore I am. Okay, I'm not going to go into the philosophy right now. I really don't know enough as well. Okay, but anyway, interesting to read up on. Right, so the reason why I mentioned Descartes, okay, so Rene Descartes, is because hidden in his name is, or hidden in Cartesian is part of his name. So Cartesian comes from Descartes. So Descartes was came up with the system of coordinates essentially with X, Y, and Z. And I think he even came up with it in a bit of a fever, and he was ill in bed, and there were squares on the ceiling, so there were square tiles, and I believe there was a fly in hopping around on the ceiling, and he decided to write down 1, 2, 3 in chalk and 1, 2, 3, 4 in order to determine where the fly was. I think that's the story. You can read up on it, and you can drop me an email and tell me that I'm wrong. Okay, right. So that's where Cartesian geometry comes from. Cartesian geometry is all about the coordinate grid. Okay, so Cartesian grid. Right, so next one then. Little diversion there. So now we've got example number 6. Right, it says example number 6, find the equation of the quadratic function whose graph is the parabola. Missed something here. There we go, those parabolas. Those are the answers. Okay, so it might be that we choose to use vertex form. Remember what that is. We could use the root form. What do they call the root form again? Called it, hopefully you got it. Intercept form is what they're calling it here. We've got vertex form, intercept form, we've got this standard form as well. Okay, so it looks to me like this is not going to be one where we use intercept form because we don't have the intercepts there. Well, we don't have the roots there, but we do in this case. But in this case, we have the vertex, so I would suggest that we use the vertex form, and we can see straight away that we're getting x minus 3 squared, and then plus 5 there, because when we put in 3, we'll get a 0 there. And when we get a 0 here, we need to get out of 5. But we don't know what A is. A is our stretch in the y direction. And in order to find out what A is, we should put in either this coordinate point or this coordinate point here. And that will help us tell what A is. So, for example, if we put in 0, that looks pretty straightforward. So if we put that in, we'll get 0 minus 3 squared plus 5, that times by A, and that should give us the answer of minus 4. So all I've done is substituted an xy coordinate point into there, and I've reduced that down to one unknown. And now I can work out what A is. So if we take the 5 off, and we'll see that we get A times by 9, so we can see that A is equal to minus 1, and we were expecting it to be negative. And if you remember my little trick that I said when I was talking around Desmos, you actually know that it's going to be 1 or minus 1, minus definitely because it's this way around, but you know it has to be of magnitude 1 there because we're going 1 across and 1 down to get back to the line. So in fact, if we'd known that little trick there, we wouldn't have had to have done this working out. Okay. Right, and with the other one, let's just clear this off. So with this other one here, we've got both of the roots, so we can put y equals 2 roots, and the roots are x. So we've got minus 3, so we're going to put an x plus 3 in there, because that will make a 0 when we substitute in minus 3. And then we're going to put in here x minus 1 for this second root, because that will make a 0 when we put in 1. Now again, we're missing our A, and we can use this coordinate point to work out our A. Now these two coordinate points aren't going to be very useful to work out A, because we'll end up getting zeros there. So this is the coordinate point which is left, which will help us determine it. Now we could choose another one if we wanted to. There may be another good point there, but we actually know what A is because here we go. We can see from the vertex to the next one along, you have to go up 2. So I can see that's actually going to be 2 there. Is our little trick, but let's just put in 6 and let's put in 0. So if I put in 0, I get 3 and minus 1. And we've got A there, and I should really tell the examiner what's going on. Let's put in 0. So now we're getting minus 6 equals to minus 3A. And so A is equal to 2 if we divide both sides by minus 3. So there we go. And now we just need to restate the original equation. So just a final thing to say is that it would be fine to leave this as y equals 2x plus 3 and x minus 1. So in that intercept form, it's fine to leave it like that, unless they ask for us to put it in a different form. Likewise, it would be fine to use the vertex form unless they ask otherwise. Okay, there's nothing wrong with this as an answer here. Let's have a look at what the book does here. Let's finish this one basically. And yeah, they've left it in the vertex form, and they've left the answer in the intercept form, what they're calling the intercept form. And the other form, of course, if you remember, was the standard form, or the general equation for quadratic. Okay, well, I'm going to stop there. A little bit about polynomials. Quadratics are polynomials of degree 2. So that's the highest power on x. But I'll stop here. This is exercise 2B, and there's actually not much to this one at all. So have a go at all of those questions there. And next we're going to move on to rational functions. Okay, guys. Well, thanks for listening in, and see you for the next one.